Hi everyone. In this video, I'm going to cover some of the basics about zero-emission vehicles quite unlike this rather nice Ford pickup truck. But in particular, I'll discuss what types of zero-emission vehicle technologies we're talking about. We'll review some of the trends in adopting those technologies, and then more briefly we'll look at the impacts. And what policies governments, whether that's state or city or federal, at the federal level, can take to promote zero-emission vehicles. We're going to hold that until our class discussion, so I won't say much about them here. So first of all, what is a zero-emission vehicle? Well, in short, it's anything that has zero tailpipe emissions of CO2 or local air pollutants, criteria pollutants in Clean Air Act terminology. So right now, when policymakers talk about ZEVs, it mainly means battery electric vehicles, but it could also refer to hydrogen fuel cells. Alternative fuels is a broader set of fuels, so essentially anything that isn't gasoline or diesel. So alternative fuels include ZEVs, but also natural gas and other technologies. Natural gas is the same or slightly worse in terms of greenhouse gas emissions, but it does normally improve local air quality. Now, the prominence of different fuels has waxed and waned over the years as different fuels get hyped to different extents. Daniel Sperling at UC Davis talks about the fuel du jour. For example, in one year, hydrogen gets the attention, and then the next year it's biofuels, and then later it's something else. And we can see this in the chart on the left, which is the mentions of different fuels in the New York Times. So in the 1980s, we see that methanol was the big thing. Then in the 1990s, the first wave of battery electric vehicles like the GM EV1. And then when those early battery cars flopped, attention turned to hydrogen fuel cells, this is this area here, and then to biofuels, and then back more recently to battery electric vehicles. And one of the constant debates in alternative fuels and zero-emission vehicles policy is the extent to which governments should focus on a particular technology. Now, having a focus in research and incentives can be helpful, especially if there's a chicken and egg problem with infrastructure like chargers or hydrogen fueling stations. But picking winners is a dangerous game. Who knows who the winners will be? You could easily back the wrong horse. Back in the 1980s, you'd have put all your eggs in the methanol basket, for example. So we'll see that some of the more recent incentive programs have been technology neutral. They just call for ZEVs, whether that's for battery electric vehicles or hydrogen fuel cell vehicles. And we'll talk about this more in class. But here's an example. In 2011, the International Energy Agency were entering a golden age of gas. And now the European Investment Bank is, well, natural gas is over. So these fuels come in cycles or fads, and perhaps battery electric vehicles will be more lasting, but that's still to be confirmed. Now, we know the acronyms can be confusing, so here's a quick guide. So by ZEV, we mean any vehicle that has zero emissions at the tailpipe. As my PhD mentor and advisor Lee Schipper said, well, they're not really ZEVs, they're EEVs, elsewhere emission vehicles, meaning that the emissions come at the power station or sometimes in the field that's growing switchgrass or corn for ethanol. But particularly for local air quality concerns, the EVs even can be an improvement even if they're EEVs. So subsets of zero-emission vehicles, we have BEVs, battery electric vehicles, like this milk float, the type of vehicle that used to bring us milk when I was growing up in the UK. And battery electric vehicle is normally what people say when they mean EV. But there's other types of EVs, for example, trolley buses, like the ones in San Francisco, are a good example. Hydrogen fuel cell vehicles are sometimes called FCVs. And then we have hybrid electric vehicles, And then plug-in hybrids, you see them sometimes called PHEVs or sometimes just PEVs. A good example is the Chevy Volt. So these hybrids and PHEVs aren't ZEVs, but you could see them as a stepping stone on that pathway. Now it's battery electric vehicles that have taken off in recent years. And in California, Tesla might get the attention. But the two most remarkable markets are China, which we see on the left chart. It's accounted for about half of sales in recent years. The US is this purple splodge here. And then Norway, which looks small on the bar chart, perhaps small in absolute terms, but it's by far the highest in the world in per capita terms as a market for electric vehicles. And in this right chart, we see the figures for cities in 2019. We have sales here on the x-axis and the market share on the y-axis. And Oslo here really stands out. And then there's a bunch of cities that have similar market shares in the 10 to 20% range. So the largest markets are some of the large cities in China. And then we have places like LA, San Jose, San Francisco, and the large California metro areas as well, large in global terms. But in the US specifically, it is largely a story of Tesla in recent years. So we have the different car makers who are selling EVs in this bar chart. And so these brown bars, these are Tesla, which is accounting for about half of the US market in 2018 and 2019, probably in 2022. But it's not just Tesla in that most manufacturers have some EV models, so just a really small share of their sales. And that's partly because of the California mandates that we'll talk about in class. And in this map on the right, this is electric vehicle shares of 2019 new regulations. And we can see again it's really concentrated in California, along with the Pacific Northwest, some in Colorado, and then perhaps some in the Northeast US. And many of these states, again we'll discuss this in class, are those that have piggybacked on California's regulations. So what do these trends mean for CO2? Well, like for like, there's normally a major reduction in CO2 emissions when going from a gasoline-powered car to an electric car. That's partly because of the inherent efficiencies of electric drive technology. There are many fewer losses in the drivetrain. There are fewer moving parts. The electric vehicle is more efficient in taking what energy is stored in its battery and converting that into forward motion. So a substantial emission reduction from CO2, also local air quality. But the other efficiency, or the other CO2 gains rather, are because the electricity grid is only partly fossil fuels. If you have a gasoline car, that's 100% fossil fuels, but the electricity grid is getting 20, 30, 40% renewables in some parts of the country. Now this image is from the MIT web calculator. You can see it yourself at carboncounter.com. Now each dot here is a different vehicle model. So the black dots are internal combustion engines, mainly gasoline. The yellow dots are electric vehicles, and the red and purple, those are hybrids and plug-in hybrids. So there's some overlap between these categories, even at the US level. So we have greenhouse gas emissions per capita on the y-axis. So there's this area where some of the gasoline cars aren't really that much worse than the hybrids and the plug-in hybrids. Here on the x-axis we have the costs for fuel purchase and maintenance expressed on a monthly basis, assuming 13,000 miles driven per year. But the grid is very different in different parts of the country. So in California, where there's a cleaner grid, these dots are further apart. The electric vehicles are much less in terms of greenhouse gas emissions. Conversely, in parts of the country where there's a dirtier grid, this is to the Midwest, where there's much more coal, there's much less difference and much more overlap between the electric vehicles and their gasoline counterparts. So certainly the grid emissions are a major factor that is affecting the relative contributions of zero-emission vehicles. But there's also other factors that affect these reductions. So vehicle power and weight. If manufacturers use the technology to develop heavier cars that have more power, then the savings in CO2 are going to be less. These calculations that I've just shown you don't account for a rebound effect, where if it's cheaper to drive, maybe it's also more fun to drive an electric vehicle, people are likely to drive more. And that might be exacerbated in electric vehicles if people think they're clean. Okay, there's no guilt in driving an electric car to the grocery store when before you might have walked or biked. That also contributes to the rebound effect, but it exacerbates some of the externalities that are distance-based, particularly congestion and road safety as well. And then there's manufacturing impacts, particularly of batteries. That'll be a major difference between the electric vehicles and their gasoline or diesel counterparts, which affect their CO2 emissions. Now, focused on the grid here, and the electricity grid, or the relationship with electric vehicles and the electricity grid is really complex and interesting. Now, these charts on the left show the daily demand profile of electricity. So from 12 in the morning until 12 at night. And we can see, not just in California, but in most other parts of the country, there's a big gap between what's consumed in the peak of the afternoon. So this is when air conditioning loads in the summer are highest, and at 3 a.m. or 4 a.m. So the time profile of charging will play a large part in how efficient electric vehicles are and the extent to which they can help the state meet its greenhouse gas emission goals. If they're all being charged at 6 p.m., then probably the state is going to have to turn to peaker capacity from natural gas to meet that demand. If they're being charged in the middle of the night, then it's more likely that they can make use of surplus renewable capacity in the middle of the night. So how electric vehicles how we can push that charging to off-peak, particularly through price incentives and different time of use rates, is a key question. Financial incentives might be part of it. Another is a smart grid, which automatically adjusts the power that's going to vehicles based on the spare capacity that's available in the grid. Or the extreme, we could even think of a vehicle-to-grid system where the connection goes both ways, where cars draw power from the grid when there's surplus power on the grid, but they can also contribute power to the grid when there's a shortage. And that could either be on a small scale for regulating the voltage, or it could be a larger scale to fill in, say, some of that afternoon peak when air conditioning loads are at their extreme. And so this charging profile and the extent to which electric cars can be charged in a smart way will in turn affect how much they can rely on renewables, which have much more variability than nuclear or fossil fuels. And it's less a technological challenge, perhaps than an incentive one. How can people be given incentives to charge at the right time of day, or allow their battery to be used to power the grid? I wouldn't say much about the technologies involved, but one part I do want to highlight is the energy density. So this is some of the basic physics. In other words, how much mass do you need to carry around for a certain amount of energy? How heavy, in short, are your batteries? And battery capacity can be measured, for example, in watt hours, so how much power you're carrying around, per kilogram, how much weight you're carrying around. So this is a chart from the Energy Information Administration that shows we have heavy storage needs or heavy fuels on the bottom and lightweight fuels on the top. So we can see the batteries do really badly on this criteria, whereas hydrogen is much lighter. And gasoline and diesel are not as good as hydrogen, but they're much better than batteries. But the weight is only part of it. It's also how much space it needs. Gasoline and diesel do really well on that account. Hydrogen and batteries are not so good. And so this is another way of putting it. This is measured in energy per litre, megajoules per litre. Again, diesel and petrol do pretty well. Hydrogen and does well on the weight criterion. Batteries do really badly on both, even though lithium-ion batteries are a big advance on, say, the heavy lead-acid batteries that were the norm 10 or 20 years ago. So with batteries, they're just awful on both counts in terms of energy density. And perhaps that's one reason why some of the Japanese car manufacturers were more reluctant to get in on the battery game, and they pursued hydrogen fuel cells instead. So with batteries, this low energy density has either translated into low range or a very large weight penalty, and then the large batteries are also more expensive. Now, improvements are coming. If you believe the tweets of Elon Musk, then the energy density of batteries could double in the next few years, but it's still going to be a long way from matching that of gasoline and diesel power. But in spite of this, we see that electric vehicles are being adopted in increasing numbers. And one of the ways to conceptualize how they might be adopted, or the speed at which they might be adopted, is through this S-shaped adoption curve, which is typical of many new technologies. Now, getting to the first 10% of a market is really challenging. For electric motors for machine drive, we saw it took a long time, 30 years or so, to get to this first 10%. And after that, the pace of adoption was much quicker, and then it levels out as it gets to saturation point. Now, some technologies have been faster than others. Perhaps more recent technologies have moved faster, but there's still this slow adoption at the start, and there's a steep rise in the middle as both consumers and producers become familiar with the technology. And there's also knowledge spillovers, in that advances by one firm will spill over to another, maybe as employees switch jobs or patents are licensed. Even the last holdouts adopt at the end. Now, these S-shaped curves are particularly visible for some of the automotive technologies. So electronic ignition had a long time to get off the ground, and then in the 1970s, then it exploded until it reached 100% of the market. And with some of the others, like air conditioning, radial tires, we see a similar disc-shaped curve. And remember that there's a survivorship bias here, in that technologies that never got off the ground at all are not represented in these curves. We don't see methanol cars here because it never even made it past the technological valley of death. Google glasses never got off the ground either. But these S-shaped curves really don't account for the role of policy and how policy can accelerate adoption and move past this early part of the adoption curve and get them into the middle part, the steep rise in the S-shaped curve, where we might expect market forces to do the work for us. And how policies can do that, well, that's what we'll focus on in class. So I'll see you then.